for being here. No. Thank you, everyone. And this is the first of 4 lectures I will be giving about Lean 4 and mathematical formalization as a whole. I will be introducing what formalization is, and we'll code a bit in Lean also during the second and third lectures. So here are the dates of the lectures. If you come to the second and third lecture, please bring your laptop because we'll be trying to code something together. You do not need to download or install anything. We'll be using the Lean web interface. And then in the last lecture, we're going to be talking about the interactions between Lean and artificial intelligence. So here are the topics we're going to talk about today. We're going to start with formalization, what it is, and why is it useful or interesting in some ways. Then the Lean 4 theorem prover, which is a specific tool to do formalization. There's others, but Lean 4 is the one that I use and which is more and more used through the mathematical community. And then we're going to see a few examples of formalization projects, usually collaborative formalization projects, which are large scale and involve many mathematicians in the whole world. And the last part will be dedicated to a few tools which can be useful while you do stuff in Lean. So let's start with formalization. Now, some of you may know what it is, but some maybe don't even have an idea what we're talking about. So let's start from the very basics. Now, let's imagine we're doing mathematics, many of you are doing mathematics on a daily basis. And what you do is you usually do a proof of some result. And we used to consider a proof like a single thing, a monolithic thing. But in reality, a proof is something we communicate. And this communication can be done in many different ways. In particular, the communication of proof can be done with different levels of rigor. So for example, we may start by telling a proof to a colleague, to a student orally, so just talking, and we may give a few details, but probably not all details. We may get something wrong, and the other person may not notice that we got something wrong. So maybe you want to go a bit deeper and do a bit more details. Maybe write something down on the blackboard. This is going to be a bit more rigorous. It takes more time because I have to write things down now. But people are going to notice mistakes and details more, so it's more robust, more trustworthy. But still, we're not going to really trust proof just written on a blackboard. So usually we write things on paper or on LaTeX, and then we publish it. Maybe first we put it on the archive. And if we really want to be sure that the result is true, we give it to some other mathematicians. They do peer review, and they tell us, okay, yes, we're convinced that your result is actually true, that your proof is sound. And usually that's the ceiling of rigor that we're going to get in classical mathematics. We're not going to get anything more than that. And okay, we've seen that the more rigor that we put into a proof, the more trust other people will give to our proof, and even ourselves. We can give more trust to the proof if we've written down every detail. But at the same time, it needs more effort, right? A more detailed proof to give a more rigorous proof. What if we want to take this to the extreme level? If we want to reach the maximum level of rigor possible, trust. So what we do is we do a formal proof, which means we decompose a proof down to its very logical, low-level steps, and we write them down one by one. At this point, we're going to take a lot of time to write this proof, but we can be more certain that it's true, that we didn't miss any hypothesis, that we didn't skip any passages. We can do this on paper, of course. We can write formal proof on paper. But is it really going to be more trustworthy than a math paper, for example? Well, I don't think so, because we're still humans and we make mistakes even when we do simple things. So even if I'm doing a proof with 1,000 steps, which are formal, there is some chance that I get something wrong. But then here's the catch with formalization. You can use tools that can help you be sure that your passages are actually true. And that's something you cannot do with informal proofs, which are proofs written in LaTeX, for example, because abstract passages are too difficult for a computer to understand. They're not precise usually. So with formal passages, you can plug it in a computer and use the computer to give you certainty that the proof is correct. Now, I said that it takes a lot of time to write a formal proof, but the computer can help us even in that matter. The tools we use to formalize proofs are called ITPs, which stand for Interactive Theorem Provers. They're pieces of software where we write our proofs down, and they basically check that everything is correct. The first thing they do for us is check the correctness of the proof using a piece of code that's called the kernel. And the kernel is usually a small piece of code that has in it the very fundamental deductions, like deduction rules of logic. So it's simple, it can be easily checked by a human, it doesn't change through time. So if the kernel tells you, okay, your proof is actually sound, you can really trust it. It's really, really unlikely that the kernel tells you the proof is right, even if it's wrong. While a human, well, for example, a peer reviewer can tell you that the proof is right, even if there's a small mistake that it didn't catch. The second thing an ITP does is it helps you write this formal proof faster. As I said, it takes a long time to write formal proofs, mainly because there's a lot of repetitive details which are not actually like bright ideas and abstract formalizations, but more pedantic details. A lot of those details can be automated through software, which produce a certificate that the kernel can then check. The part of software that does this is called the tactics, which are automations. There's a lot of different kind of tactics in Lean, for example, but also in other theorem provers. And each tactic usually helps you with some kind of automation. For example, there's tactics that help you prove that something is continuous. For example, let's say you have two continuous functions. You have the sum of those. You want to know that the sum is continuous. You can do it by hand, or you can just call continuity. And if you know how to do very simple deductions like this. Now, here is what a Lean proof looks like. It's not readable, doesn't matter. It's just to show you that we're talking about some software interface. We're writing code. Proof in this regard is exactly like code. We are actually coding the proof. And so we have our interface. Here we write the code, and here the interface will give us some useful information about the code that we've written. So what do we do when we actually formalize something? What's the practical steps that we take? So first, we should formalize. Let's say we want to formalize definition, or maybe it's proof of a theorem, or maybe it's a statement of a theorem. So we decide on that, and we write it down in the interface that you've seen before. And we have to use a very precise syntax because we're coding, so we cannot just write in natural language. We use keywords and a rigid syntax so that the computer understands what we're saying. And it looks like this. So you can try to read what's in there. You see there's written theorem, which means, okay, we're starting to write theorem. Then we say how we're going to call the theorem, because maybe we want to reuse the theorem later, so we have to give it a name. In this case, add sub pencil. And then we write what the actual theorem is. We start by introducing some variables here. A and B are real numbers. And we're saying a very simple thing, which is B plus A minus B is equal to A. It's a very basic result. Then what we write is the proof of the result. And here we're just substituting various other lemmas that we've formalized before until we arrive to a goal that's trivial. So basically how the formalization usually works is backwards. Start from the goal, which we want to prove. We simplify the goal until it's simple enough to be just trivial. But we'll see more details of that later. Once we've written something in Lean, Lean automatically checks it for us So it checks that we've written things that are correct, both syntactically and semantically. What do we mean by that? Well, we can of course write just English in Lean, but will not check. It will not type check. It will be just wrong syntax, and Lean will tell us, okay, it doesn't make sense. But we can also write things which are correct in syntax. Maybe I write, okay, 1 is equal to 0. It's perfectly legitimate to write 1 is equal to 0, as it's legitimate to write on paper, for example. But once we go to prove it, once we write a proof, we're going to find that we cannot prove it. Or if we're convinced we can prove it, we made a mistake. And if we made a mistake, Lean will tell us that we made a mistake, and it will tell us exactly where we made the mistake. As I said before, the kernel is the part that checks that we didn't make any mistake. It's more unreliable because it needs to be checked by hand once, and it's already been checked by a lot of different computer scientists. And then it's stable; it doesn't change, so we don't introduce bugs during the development. And you see, if I write something that's wrong, for example, here I'm writing that okay, I can prove this fact just by using this theorem here, but it's not true. It's not, this theorem doesn't prove this fact. So Lean will tell me, oh, there's a type mismatch, which means there is something that doesn't add up correctly. Now, Lean does not only tell us when we're wrong. When I write a formal proof, I like the computer to help me, not just to be a teacher that tells me, oh, you're wrong, but also to be a companion that helps me both write the proof and understand the proof more deeply. In fact, we can, for example, hover over any object that's written in Lean, and Lean, which means like putting your mouse over the object, and Lean will tell us additional information about that object. And it looks like this. So here we're saying, okay, measurable space alpha. So alpha is a measurable space, but maybe I don't know what a measurable space is. Maybe I don't know how it's defined. So I can just put my mouse here, and it tells me, oh, a measurable space is a space with sigma algebra. It has this type, and I can constantly click on it to jump to the actual definition of, for example, a measurable space, but it can be a theorem, a definition, whatever. Moreover, while we write the proof, Lean tells us information not only about the object that we see written on the IDE, but also on the context of the proof. Now, what is the context? Let's see an example. If I put my cursor inside the proof, I'm going to see something like this. This tells me what are the things that we've defined until now, what are the variables that we have at hand that we can use. In this case, we have A and B, which are real numbers. And what are the hypotheses that I have, which I can use? So I have that A and B are positive real numbers. And at the end, it tells us what is the goal that we still need to prove. This is the symbol for goal. So here we have to prove that 0 is less than A plus B. So sum of two positive negative numbers is the. While we go through the proof, this goal will probably be simplified more and more easier and easier to prove. And we have more and more hypotheses because we will prove like intermediate facts. Now, I told you what formalization looks like a little bit, but I didn't tell you why it's useful in formalization. So let's see a few reasons why we should do formalization. And by the way, if you have any questions, like interrupt me whatever you want. So I took this the idea for this slide from Pietro Antigone's presentation a few months ago. And the first thing that comes to mind usually is verification. So we want to formalize, which is also the thing that I told you before. We want to formalize things because we want to be extra sure that things are actually true. We want to check that the results are true. We want to catch mistakes if there's any. We want to fix them, and we want to fix the gaps are there. Maybe there's a theorem which has like kind of just a sketch of a proof. There's a gap. Are we really sure this gap is fillable, is true? Most of the times we are, if that's a peer-reviewed result, for example. But there's examples of false peer-reviewed mathematics, or proofs which are true in the end, but have some false passages which have to be circumvented in some way. So that's one reason. But most mathematicians will tell us, okay, yes, but we know that most mathematics that we publish is actually true. Maybe there's a very few small mistakes here and there, but I don't really care about verifying everything. So let's give a few more reasons why formal verification is interesting. But formal verification gives you more insight in some ways into the proofs. Why? Well, because when you have to spell things out very in a lot of details, it's very frequent that you notice something that you didn't notice when you just skip over and try to go fast to the end result. It gives more clarity to the proof, also to people who read it. Maybe I'm not an author, I'm reading a paper which is not in my field exactly, and there's some passages that the paper gives for granted, but I don't really understand them. But if I'm reading a proof that's formalized, everything has to be formalized. There's no gaps allowed because the kernel will not allow anything that's not signed and complete, which means I can inspect the proof. If there's a definition I don't understand, I can jump to the definition, and everything is there. I don't need any external resources to understand the mathematics that's there. Another reason is generalization. So let's suppose I have my theorem, I published my theorem, and everyone loves it, everyone uses it because it's a great theorem, and a few years pass by. Then another person comes up and says, "Oh, look, your theorem actually has an hypothesis that's a bit too strong. It can be made weaker. So actually, here's a generalization of your theorem. What about all the people who use my theorem? Are they going to benefit from the generalization? How are we going to propagate this generalization? It's going to take a lot of time, and probably in many cases, it will not be propagated. If we have our proofs formalized, once we generalize a theorem, so the theorems below it need weaker hypothesis, the system automatically tells us, hey, here you put an X hypothesis, you're not using this hypothesis anymore. And so we can just remove it very quickly and generalize everything that depends on a single result. Also, there's a few automations inside Lean that make it very easy to link things that naturally depend from one another. For example, I have a space which is a metric space, and I want to know that's a topological space. I don't even have to write it down. Lean knows it automatically that it's a topological space, and this works for much more complicated structures. Lean also helps us to manage complex mathematical objects because it keeps track for us of all the variables, all the theorems, all the hypotheses that are needed. So it helps us to manage complexity and we can work with a feedback that's real time. Each time I write something in Lean, I don't need to complete the proof. Each time I write a single line of code in Lean, it's going to tell me, is it true, is it not true, is there some missing hypothesis or not? So I can check things at the time I think of them, at the time I write them. While this is not, of course, true for general mathematics, because the feedback is usually either myself who check the proof again, or other people who check the proof for me, which takes months or even years. And we go to another point, which is collaboration. So a very important thing is accelerating the review process. Basically, as I just said, the review process in mathematics takes forever, even years at times, and it could be made much faster if the result formalized. Because once I have a result formalized, nobody is going to have doubts about truthfulness of the proof. So the only role of peer review at that point would be to check that the definitions make sense, and maybe that my theory is actually an interesting theory, that it's something that's worth reading for others. But the proofs will be just straightforward. If it compiles, which means if Lean tells us it's okay, then it's okay. If it can be used also for teaching, for example, it's been used already for some years in a few universities around the world to teach some courses. It's especially useful for logic courses, but also introduction to proof courses. But it's starting to be used also for more advanced courses because we're starting to develop a more advanced library that allows us to talk about complex objects. And another thing that's super, super interesting, in my opinion, is that we can collaborate with a lot of people. So collaboration in mathematics is usually very, very small scale, even compared to like any other scientific research area, because you usually collaborate with 2, 3, maybe up to 5 mathematicians in some occasions, but very rarely more than 5. Formalization allows you to extend this number like 10 times, 100 times. But why can we collaborate with more people? Well, the key point is trust. Because when you work with someone, you need to trust his work. You need to trust that he didn't make mistakes. So one of the main reasons why mathematicians only collaborate with few people is because we do not trust like a random person who is not even an academic to do the proof for us. If he does, like if he proves a lemma, we're just going to take more time to check the lemma is true than we would have taken to prove the lemma ourselves. Right? With formalization, this trust problem is completely gone. Let's suppose, for example, that someone who is not from academia, just maybe or an undergraduate student wants to collaborate to some research project. He takes a lemma that's still not proven, but he knows it's needed for the project. He manages to prove it, and then the proof is a certificate itself of the truthfulness of the lemma. It doesn't need anything else. We don't need to rely on how the author is known, or if the author has or has not any mathematical skills. Because if you manage to prove it, that is true. And we will see a few examples, mainly one example of this large-scale collaboration later, which actually, so it's not just in theory. There's actually people who collaborated on large scale, more than 50 people, to do mathematics together and to produce new mathematical results without ever meeting each other. With formalization, we can also organize large-scale libraries, so we can create a corpus of mathematics, kind of in a fashion that reminds a bit of Bourbaki, so some kind of like one source to know everything about mathematics, or at least the fundamentals, the things that everyone uses. In Lean, that's called Mathlib. There's a single library that contains all of this. And it makes it very easy for other people to use your code. So once it's proven a theorem, it's not just for me and maybe for the few people who know my paper, but the theorem is for everyone to use. And one thing that's also useful is to look for things, because again, if you have things just deep down in the archive, deep down in papers, it's not really easy to look for specific results. While if you formalize things, they're very much easier to search using both search engines, which are like classical search engines. Maybe I just look for a particular string or for a particular regular expression, but also using more advanced search engines, which take also into consideration semantics. For example, there's a few LLM-based search engines to look for results on Lean. And the last thing is, I think one of the most important things, aspect of formalization, is it enables us to talk about mathematics with a computer in a way that we can trust each other. So we can use AI to do mathematics, and we can use mathematics, so we can use formalization to enhance the performance of AI. We'll see a bit more of that in the last lecture. Now, as I said, Lean is not the only theorem prover out there. There's more examples. I will list just a few of them quickly here. The first interactive theorem prover was called Mizar. It was based on set theory. Then there's Isabel, which is still used nowadays. Its logic is a bit simpler than Lean, a bit more less expressive than Lean, but it's still useful to do a lot of things. There's Coq, which has been recently renamed to Rock, and this is probably the most widely used after Lean. It's been around for 30, 40 years now, and it has a little bit less mathematical friendly notation, but it's still very powerful, and a lot of results are still being proven it. For example, the busy beaver number, which is the exact number of busy beaver 5, has been proven to be an exact number in just a few months ago in POC. So it's formally proven to be like 41 million something. Then we have MetaMath, Agda. I'll mention Matita because it's been developed here in Bologna actually, around 2003 by the computer science department. And at last we have Lean. Now I put this in chronological order. So Lean is the newest of them. And it's also the one that's mostly used by mathematicians nowadays, and it's been experiencing the most growth. So why did I choose to use Lean? Why should you also choose to use Lean? Well, because it's modern, it has good tools, it has very user-friendly tools compared to the others. It has strong programming capabilities, which means I can program things in Lean itself. For example, I can program automations to do proofs. Maybe I want to do a new automation that proves, I don't know, measurability of stuff. It exists. I can do it completely in Lean without resorting to third-party, to third languages. Maybe the most compelling reasons to use Lean is because of its mathematical library. So when you do mathematics, of course, you're going to rely on lower level mathematics, which relies on lower level mathematics and so on. So you're going to need a lot of stuff in the background before you start using like Lean for your research purposes. So having a very good and very well maintained and updated library is a very important thing. And Mathlib is this, and it's growing more and more. It has a lot of mathematics. It has almost everything, not really everything, but most things on the classic undergraduate curriculum, and it has also a lot of more advanced topics here and there. Also, there is a very active and welcoming community. If you're going to start a project, there's lots of people on the Zulip channel, for example, which I'm going to talk about later, who's willing to help you get started and even help you with your project. And it's very mathematically friendly. We see later, I mean, we already see, maybe you didn't know this, but we wrote R, as in the field of real numbers, with the mathematical notation. We did not write like real. We wrote with the Mathlib R. And that's because we can use Unicode notation inside the code. So we can write the integral symbol, we can write derivatives inside the code. So it's very more, it's very much easier to read compared to like reading things in normal computer programs. So let's go more deep into Lean 4 itself. As you think, this is the logo of Lean. And Lean, first of all, Lean 4 is a computer programming language, which means it's just like C++, just like Pascal or Rust. It's some language in which you can write commands for the computer to execute. In theory, you could write everything that you write in like JavaScript in Lean. It's Turing complete, you can do everything. Of course, it's not practical to write websites or video games, but it's still doable. So it's very flexible. What really matters to us, though, is that it's also an interactive theorem prover, also called a proof assistant. So it's a piece of software that helps us write mathematics formally. Now, the interactive theorem prover called Lean is a software written in the Lean 4 language. That's a new thing, actually, also for Lean, because Lean 3, for example, the previous iteration was not written in Lean. It was written in C++. So that's a new thing, which makes a lot of things easier, a lot of metaprogramming easier, and everything runs a bit smoother. The first release of Lean was in 2013 by Leonardo De Mura, which was at the time a computer scientist at Microsoft, and now is at Amazon Web Service. And now we're at its fourth iteration, which appeared in 2021. It took around 2 years to be actually taken up by the community, because there was a transition to be made between Lean 3 and Lean 4. A lot of theorems that were in Lean 3 had to be translated in Lean 4. But now Lean 4 is the state of the art. Everyone uses Lean 4. Lean 3 is basically just a legacy. just legacy system. As I said, we can use it to formalize and verify mathematical proofs. Now, Mathlib, I already mentioned it, is really the backbone of any project that's written in Lean. It's a mathematical library, and I'm going to explore it a little bit. Yes, basically, whenever you do mathematics that's not like very, very basic logic and Lean, you will need Mathlib, because maybe you need real numbers, maybe you will need functors between categories, maybe you will need something about algebraic geometry that's already, and you don't want to formalize it by yourself from scratch. It's an open source project also, so it means that everyone can see it. It's community driven, which means that everyone can contribute to it. It's a very welcoming project, so if you want to contribute to Lean, the community will help us. It will help you get up to speed to write code that's suitable for Mathlibs. And right now it has more than 500 contributors that have actually put some code, some mathematics into Mathlib. Now, a small caveat for Mathlib is the code in Mathlib is of very high quality. It has very particular standards to be accepted in Lean because of two reasons: maintainability and efficiency. So Mathlib has become quite big project. It's around 5 gigabytes of data. So we cannot really afford having inefficient coding because it would take forever to compile. So there's a lot of techniques that can be used to make it faster. And usually the code is required to be quite clean. The proofs are not so easy to read. So if you want to try and read something in Lean, Mathlib is not always the best place to go, like for a very beginner, because the notation that's used is very compressed, is a bit hard to read. But if you want to contribute to it and you have like not very clean code, you can do a PR and people will help you clean your code, will give you suggestions on how to make your code faster and better. That's the face of Mathlib. We can say that's the graph of all the files in Mathlib. It's actually like 2 months ago, but it didn't change so much by then. You can see different colors relate to different areas of mathematics, and each point is connected to the others when there's an import. So when a file imports another file, so it depends on the result of the other files, we import that. And we can see now, you cannot really see what's there. We're going to see this same graph, but interactive in a minute. Let's go and have a quick look at what's in the library, in Lean Library. Now that's a Lean community website. That's a very useful place if you need anything about Lean. There's most things about Lean are here. One of the pages is this Mathlib overview. This is not trust it to see if your favorite result is in there, because it may be in Mathlib but not listed in here. That's just a very high-level overview, not updated every day. But still, you can see there's a lot of results. Here we have general algebra, linear algebra, topology analysis. You can see there's probability. It's not very developed. It's a bit small. Geometry, combinatorics. There's a few things about dynamics, data structure. Okay, and these are more technical things. So if you want to if you wonder, okay, what's there in analysis, you can just have a quick look here. You can see that Hilbert spaces are there. There's a few things about complex analysis and stuff. Let's take a look at another page of the Mathlib community's website, which is some statistics about Mathlib, just to see how big it actually is. So here we can see the number of definitions and theorems in Mathlib. There's around 100,000 definitions and more than 200,000 theorems, and more than 500 people have contributed to Mathlib. Here you can see the growth of the library. Here it's starting in 2017, because that's when basically the Lean 3 started to be a bit more relevant. And you can see that the blue line is Mathlib 3, so the old system, while the red line is Mathlib 4. And here basically is when the community was doing the translation between Lean 3 and 4. That's why Lean 4 was growing so rapidly, because it wasn't like new mathematics, it was just translation. And it's been growing very steadily for the past few years. That's the number of files are the same, but number of lines. And you can see here, we can find the same graph that we've seen before, but mostly. For some reason, it is in dark mode. And if you wonder, okay, where is like probability theory? It's down here. You can see measure theories here, so it's quite close, and you can explore like how Mathlib is done, and you can even click on single data, single points to go to the page. Now, I just click on a random point here, and it brought me to the multiset coercion to type. So there is some code about this thing, which is about some multiset. We don't need to understand what's written here now. But basically, everything that's in Mathlib is searchable through this documentation. We have here all of Mathlib, all the different folders. We can go into like, I don't know, algebraic geometry, affine scheme, and we have the page about affine schemes. Here's the definition. And here we can see a few theorems about that. Okay, let's go back. Presentation.
Can I ask a question?
Yeah, sure.
So you mentioned that like there is still 200,000 theorems, the 5 or 600 contributors, which means that like on average the contributors contributed like several hundreds of theorems.
Yes, that's true. Now, the number of theorems, now don't think of a theorem as like Fermat's theorem is a theorem, no, sphere aversion theorem is another theorem. A theorem means a lemma. So there can be hundreds of lemmas, which are just auxiliary lemmas for maybe a single definition. So for example, I introduce my exponential function. I will be giving at least a few dozens of lemmas about how the exponential function behaves, and maybe I will say, okay, it's always negative, it's always positive, it's monotone, and stuff like that. So there's also like auxiliary results which blow the number up a bit with respect to what you would consider if there is just if it was just big theorems. And also there's a few theorems which are automatically generated. That's another feature of linear. So let's say, for example, that you prove a theorem about groups in the multiplicative notation. If you get automatically translated in the additive notation, and all the lemmas that depend upon it will get automatically translated. And that's useful both for like not having to duplicate the code manually, and also to have a library that's balanced, so that we don't forget to add a result which is basically already proven in a notation in the other. So yes, there's also a few things which are automatically basically generated. But that's all automation done algorithmically. There's currently more like AI-driven automation in this regards.
And sorry, there's also a distinction between lemma and theorem, right?
Basically, it's okay. There is, we'll see something, but basically, I can show you in the interface. So let's see here. Okay, that's just the web interface that we're going to use for second and third lectures. I can write theorem like I have x, which is a real number. No, true, which is just a theorem that says I have a number. True, which is always true. I can say by careful, and this is exactly the same as this. I mean, Lean doesn't see any difference between theorem and lemma. It's mainly used because inside of Mathlib we try to give lemma to lemmas and theorem to like big results. So they're a bit easier to search, but there's no like true difference. There's a third thing we can write, which is example. Let's just copy this. That's slightly different because a theorem, I can give a name to a theorem, my theorem. And so later I can call my theorem like here. Let's do check. Check is used to like check that the type, what is the type of some object inside Lean, and I can write my theorem, and okay, the server that's stopped. Sorry. So if the server has stopped, that's just a text editor. It's not going to compile anything. Okay, maybe I have to. Yes. Okay. Okay, it doesn't work. Okay. Actually, here Lemma complains because you have to give a name to okay, so I was saying the difference between a theorem and example is that theorem you can actually give it a name. Example is just something that is not meant to be used later in the code. So maybe I'm just trying to see if something is true. I'm not going to like leave in Mathlib, so I can avoid giving name to this. But basically, yes. And oh yes, and I was saying my theorem is a name with which I can reuse the code I've written. So if I go here and I check my theorem, it's going to recognize it. It's not going to say, okay, I don't know what this is. Why if I write some random thing, it's going to say, oh, I don't know what this is. But yes, theorem and lemma is just notation, really. Okay, let's go on and let's try to see now. I've written some code, but you will not have understood what's written in there. So let's try to understand how to read Lean code. And before I say anything, I would just like you to try and understand this by yourself and see if you can read what's written there. I mean, perfectly the web already written Lean code. Okay. If anyone has like any idea what did that mean? What does it mean? What am I doing in here? Okay, let's go see what we are actually doing. We're defining what a measurable function is here. Okay, we're giving a definition. In fact, we have the def, which is the keyword for with which we're saying to Lean. Okay, now we're starting a definition. So this is something that you have to remember, and that's defined in this specific way. Theorem, lemma, and example are keyword, just like def. So we could have written def exactly like we could have written like theorem, my theorem, etc. Then we say how our definition is called, which is measurable in this case. That's the name of what we're defining. Then we have a few things which are between curly braces or square brackets. And these are the implicit hypotheses. What we're saying here is alpha and beta. We're introducing alpha and beta as type. We'll see a few details about what type means later. Let's just think them as if they were sets. So we're introducing these two sets, alpha and beta. We're saying that they are measurable spaces. And we're using implicit hypothesis because we don't want to tell what alpha is, what beta is, and the fact that they are measurable spaces each time that we call measurable. Instead, what we're going to give to measurable is the function. Because of course, if I just write measurable, how will you know which function I'm referring to? So I have to give f as an argument. So I put it in between parentheses. So it's an explicit argument. Lean will ask me actively to write it down. But if I've written f, Lean already knows that f is a function between alpha and beta. So it will be able to infer what alpha and beta are, and it will look into the context to see if alpha and beta are already declared to be measurable spaces. And so it will not even ask me, oh, show me their measurable spaces. It will already know it. If it doesn't know, if it doesn't match to it, of course, it will complain and tell me, hey, I cannot find the measurable space instance. Please provide it to me. And finally, we have the column. And then there's prop written. Now the column means all this stuff we're writing here is of type prop. and again, we'll see what it means later. A prop means it's a proposition. Okay, we're not defining like a function. We're not defining a structure over some set. We're defining a proposition because the fact that f is measurable is a proposition. Okay. And what is this proposition? What is the mathematical content of the proposition? This is everything that's written after the column equals sign. And I think you can read it quite easily. We're saying that for every t, which is of type set beta, which means it's a subset of beta, if t is a measurable set, then the counter image of t with respect to f is also measured. Okay, that's the standard definition of measurable function. Let's see a second example.
Yes, but in that part, the f from alpha to beta is something that is. I can say that measurable set, measurable space is something you have defined on Lean.
Yes.
And once you have defined it, you can use measurable set for defining measurable function. But the notation f from alpha to beta is something you have also defined as a measurable set.
No, this is not. So the functional notation is something that's primitive to Lean.
Okay.
We'll see just a few hints of this in a few minutes. And that's because we're using this type theory and not set theory. Now, in type theory, functions are a primitive object, while in set theory, in the first lecture of algebra, in the first year of undergraduate, someone will tell you that function is just a Cartesian product, blah blah blah. In type theory, this doesn't exist. You don't have to define functions; they're already there in the very basic theory that you're using. Okay. Do you want to make a small break, like 10 minutes break? Okay, I think we can start again. We were talking about, let's try to understand something written in Lean. We've seen the definition, we've seen the definition of measurable function. Now let's see a theorem instead. Of course, theorem has two different parts than definition because we have to give hypothesis and a proof. So let's see how to read it. This is, if I remember correctly, it's the same theorem I've shown you before. So it's a very basic theorem, which says that b plus c minus b is a. And how do you read this? Well, we start with the theorem keyword. As I said before, if we written lemma here, it would be exactly the same thing. We're just saying Lean, okay, we're starting, we're going to give you a theorem. Then we give the name of the theorem, just like definition, theorem set names. In this case, we only have explicit hypothesis, but not the general rule. That's just that this theorem in particular doesn't have any implicit hypothesis. So everything is explicit. When I call the theorem, I will have to explicitly give to him what are the two real numbers which I'm referring to, which I wanted to apply, which I want to apply it to. So in this case, we have A and B real numbers. Then we have the column, and we have the content, like what we would call the thesis of the theorem, which is that B plus A minus B is equal to A. Now, whatever is after the column should be a proposition. Okay, so it should be. We will not write like a function there. We will not write a structure there. We write something that is a proposition. So something that can be quantified. For example, we can put implications there. And in this case, okay, it's very simple, and we can prove it then. So a theorem, as you know, is both the hypothesis, the thesis, and the proof. And so, like in mathematics, and so is in Lean. And the proof is written after the column equal by. And now by is another keyword in Lean. By is used. Okay. By is used to introduce what's called the tactic mode. Now, there's two different ways of proving things in Lean. I think we'll see a little bit more about this in the next lecture. But basically, you can either give explicitly the proof, like the applications of theorems explicitly to Lean, and in that case, you don't need the by. Or you can use a more interactive mode, which is called the tactic mode, which can use the automation I talked about earlier to help you handle the proof in a more human-like way. So in this case, we are into tactic mode, and we're doing some stuff. In particular, we are using RW, which is rewrite, which means, okay, I have a theorem that has some equality. Please use this equality to rewrite, maybe find the left-hand side of the equality in the goal, substitute it with the right-hand side, but we'll see more details about this during the actual tutorial. Basically, all you have to know by now is that after the by is the proof component. And it has to type check. It has to be a sound proof so that Lean doesn't give me an error. If it's not sound in any way, Lean will stop. Okay, so let's talk a little bit about the logical foundation of Lean. I mentioned before that Mizar, so the first theorem prover, was based in some axiomatization of set theory. Now, more modern interactive theorem provers tend to be founded based not on set theory, but in type theory. In particular, there's a specific type theory which is called dependent type theory, or calculus of inductive constructions. That is a specific theory that's used in Lean. This is also used, for example, in Coq, which is one of the provers I've shown you before. Let's see how it's different from set theory, and if it will really matter for us as mathematicians. So we start by saying, okay, usual mathematics, we start with sets, which are just collection of things, and they are the most fundamental object that we use. And everything in mathematics, if we are pretending to be using like ZFC, for example, the Zermelo Fraenkel with choice, everything is a set, meaning that really everything, like the numbers, are actually formalized in set theory as sets, because everything that exists is sets. So we can compose them in various ways, but everything just turns out to be a set. Now, in type theory, it's kind of the same thing, but with types. We call them differently. So what a set is in set theory, it's a type in type theory. It's a collection of things. But if it were exactly the same as set theory, we would not even make the distinction, right? So there must be some caveats. The first thing that, and probably the major thing that differentiates set theory with type theory, is that a term can have only one type. While in set theory, we know that an element can be an element of multiple sets, like a number, which is not a number, is also an element of the integers, of the reals, of the complex numbers, and so on. And there's no problem with that in set theory.
What is a theorem?
Also, a term is, let's call an object in our theory. Basically, almost everything is a term in set theory, in type theory, sorry, because even types can be terms of other types. Okay, so let's just think of it as object. And as I said before, functions in type theory are actually.
When I say term as a unit type, means term is an object of the collection, the collection.
Yes, exactly. So let's say I will actually. Okay, let's start right now to write something. Let's see if I can share this other screen. So let's say we want to compare. We have a set, and from here we have a type. So with a set, we say that like X is an element of some set S. With a type, we say that T is of type T, for example. Okay. So the notation is slightly different. We use the column notation. And then if we have another set here, let's call it S prime, there's no harm in saying that X is an element of S prime. That's perfectly legitimate. Maybe it's false. It can be a false statement. So I can write that I know 1.5 is an element of the natural numbers. That's false, but that's correct. Meaning that that's syntactically correct in set theory. There is no harm in writing that. Nobody will complain. I mean, maybe someone will because it's false, but I can say a false statement is 1.5 is in n, and that's okay. What I cannot do here instead is, if I have a type t prime, I cannot write this, meaning that Lean will not just tell me it's false. It doesn't know what's false and what's true usually, like just from scratch, but it knows what doesn't type check, meaning what does not have the correct type. And if I already wrote this in here, it knows that T is of type T, and T cannot be of type T prime. That's not even a correct statement to make. It's not false or true. It's not syntactically correct. So what do we do if we have to talk about things which are like which we think about as elements of different sets? As I mentioned before, a natural number, there is a lot of times which I need to see it as a complex number, for example. So what do I do? Well, I use what's called a coercion. Let's say I have a number n, which is of type n, and I want to use it, for example, inside the sine function. Okay, I have defined somewhere the sine function, which goes from R to R. Now, can I write sine of n? Is this syntactically correct? Well, here's a caveat. Because in just basic type theory, this is not acceptable. That's wrong. Like Lean will tell you, why are you putting a natural number where a real number should be? It's like putting, I mean, it has the same reaction that we would have if we put, I don't know, a function inside the sign. Like, what's the sign of exponential? It doesn't make sense, right? But we know that it kind of makes sense still to take the sign of 5, for example. So there's some automation that goes on inside Lean to make this easier for us. So that in Lean, sin n is something that we can write just because Lean makes the extra step for us of converting it to sine of, let's write it like this. This is an arrow that goes up, and it's how coercions are usually shown. This just means this is not n, because n is in n, but I have a coercion, so a function that goes from n to r, and Lean automatically applies it to n if it knows it's expecting a real value instead. So this is something that is different, but we don't really have to care about it. At least most times we don't have to care about it. There's some specific times where maybe there is a coercion, but Lean will not be able to find it, maybe because our expression is too complicated. And in that case, we may write something like sine of n as a real number. So I'm telling you, okay, look, convert it to real number. Please look for the conversion, for the coercion from n to r. Or if really it cannot find the coercion in any way, we can give a name to the coercion. Let's call it sigma from n to r, and we have to write sigma of n explicitly. But this almost never happens. It's very, very rare that we have to explicitly give the coercion to Lean. Okay. Now another difference. Okay. Well, let's say here. Another difference between type theory and set theory, which is a bit relevant, mostly to understand the notation of Lean, is that in type theory, propositions are type. Okay, so in set theory, usually we think about propositions as something that's external to our to the universe our objects live in. It's something that we use to talk about our sets, our objects, but they're not sets, propositions themselves. While Lean propositions are types. In particular, they have the type prop. So they have P, which is a proposition, is of type prop. Maybe P is defined.
Prop is not like theorem named by the
No. A prop is not a keyword. Prop is, I mean, okay, can be considered a keyword, but it's not a keyword in the sense that def is. It's the same as okay. We've seen before, like alpha beta type, like type asterisk. This type is the same as this prop, so it's a type. In general, it's a universe of types. For example, when you write types, when you write prop, it's just a single type. And for example, let's say that P is a proposition about natural numbers, something like for every n natural number, I have that n is greater or equal than 0. Okay, so that's the content of the proposition. This is P, and it's of type prop. But P is a type itself. Okay, as I said before, types can have types. So we can have nested types. So we can have an element of type P. And you may ask now, what does it mean? What is an element of type a proposition? And that's a very cool way of seeing mathematics. I think that's very nice, because X in this case is a proof of P. So elements of type P are proofs of that proposition. So X will be a sequence of steps, for example, that proves that for every n, which is a natural number, n will be bigger, greater or equal than 0. Now, what if a proposition is false? What does it happen when a proposition is false? Well, it's very simple. It will have no proofs. So the type will be empty. So false propositions are those propositions in type theory which have no terms, which are empty. While true propositions are all those propositions which have exactly one element. And that's another caveat. Exactly one. Yes, exactly. That's the usual thing, but I can prove a theorem in many different ways. But there's a thing in that theory, which is that every proof is exactly the same as any other proof. They are all just different ways of writing the same object in type theory. This is called proof irrelevance. So the different proofs I give of a single statement are irrelevant. Lean does not know how I prove something. I mean, it does know how I prove something, but when I use a theorem, it doesn't care how that theorem was proven. It just cares that there is an element of the type, that the type is inherited. So if there is at least one proof, if there is more than one proof, we don't care. They're all the same, exactly the same. Yes, and that's something that it has to be digested by a mathematician because it's something that we're not completely used to. But it doesn't change anything. It's basically harmless. In when using Lean, there's no reason why we would like to have different proofs in practice. You can of course still formalize different proofs of the same theorem. You will still have the formalization. You still have the assurance that that particular proof is true because it compiles. So you can have different proofs, but Lean will not care. It will just tell you, okay, yes, they're true, but I don't see the difference. Okay, and just to get a bit more acquainted with this proofs as types, let's try to see how different combinations of propositions behave. Of course, in logic, we can combine propositions in various ways. For example, we can say that if we have P like prop and have Q, which is prop, so two propositions, we can have P and Q. So we have P and Q. This is, of course, still a proposition, like a prop. And what if we want to prove P and Q? Well, to prove P and Q, we have to provide a proof of P and a proof of Q. And that's kind of analogous to, so we have basically give a pair of proofs, right? So it's just like doing the Cartesian product of P and Q. So this is kind of similar to having P cross Q, right? What if I have to take an OR? So P or Q is the prop, of course. And what does it resemble? So I have to give either a proof of P or a proof of Q. So basically what you're looking at is the union, this joint union of P and Q. So this is kind of like the union of Q. And what I think is the nicest is an implication. Like what does it mean that I have to prove P implies Q. And that kind of answers more deeply your question before. Because what if I have to prove P implies Q? Well, I have to say, suppose P is true, then Q is true, right? But suppose P is true means suppose that we have a proof of P, then I can provide you a proof Q. What is it? It's just a function that takes an element from P and gives you back an element from Q. So this implication here is a function from P to Q. And that's part of the reason why functions are really primitive objects in type theory. Okay, we don't have to we don't need to define them because they're really needed to manipulate the very basic objects of type theory. And that's exactly the same function. I mean, that's exactly the same thing as taking a function from N to R. That's just function. It's something that takes an element in the first type and gives you an element in the second. That's the same as doing an implication. And now just quickly, let's see, we can also do quantification. For example, we can say there exists an X in like some type X, I mean X, which is type, then P of X. I mean, we have an X such that P of X. For this, we have just to provide basically the pair of an element of X and a proof of P of X. So we have to provide a pair, but that's not a Cartesian product because the second element, what goes in here, is not a fixed type because it depends on the first element. So I have to give basically, that's basically a dependent type, okay? Because the second part of the type depends on the element of the first type. And that's why it's called dependent type theory. And that's, I think, a bit more like apparent when we look at the for all quantifier and say for all X in X, P of X holds. What I'm doing here is actually I'm just doing an implication in disguise because I have to take an element of X and provide you a proof of P of X. Now, maybe I've been a bit naughty with the notation here because I'm using P again, but in this case, okay, let's change the notation here. Let's use something else like F, because in this case, F is not a prop, but it's a function of X prop. So for every element of X, it gives us a prop. And so to prove this, for example, we need to provide a function that takes an element from X and gives us proof, so some proof in F of X. So it gives us a prop, and that's also a dependent type, okay? Because we have to take something, and the thing we give back, the type of the thing we give back depends on the. Again, that's why it's called dependent type theory, and that's much more expressive than non-dependent type theory. It allows us to actually write modern mathematics. Otherwise, we couldn't write modern mathematics with type theory, like everything that's written in papers. It's really impossible. So let's go back to sharing this. Let's see if it works. Does it work? Showing. Let's try again. Okay, that's what it works. Okay, so as I said, the things to keep in mind are mainly each term has a unique type, so you may need to use coercions, but they're mainly used by Lean itself, so you don't need to worry too much about them. Propositions are types, so a proposition P is a term of type prop, and a proof of P is a term of type P. So we can even go back to this, for example, and we can see that we're basically defining a term of type B plus A minus B equals to A. You see, we're using the same notation with the with column, and we're saying that add subcancel A and B, so all this stuff is a term of this type, which is of type prop. I mean, b plus c minus b equals a is a prop. And after the column equal, we're telling it how do we define actually, how concretely, how do we construct this specific term of type of this type. But again, once we've constructed it, Lean doesn't remember how we constructed it because it's exactly the same as any other term of type b plus c minus b equals a, because there's only one term this type. Okay, now that we've seen like what formalization is, how to write, like how to read things. Yes.
Yeah. The real number set it's something that Lean has already is something primitively.
No, real numbers are not primitive in Lean. They are defined. I think currently they are defined like with the full analysis notation as equivalence classes of Cauchy sequences. So just like you would see in an analysis textbook. So someone somewhere has written all of this down in Lean, and now R, you can also call R like real, like REAL. But then they wrote an abbreviation or a notation for Lean for R, so that whenever we write R, Lean knows that we're talking about real numbers. You can define custom notations with any Unicode symbol. So you can put, we're going to see a bit more at the end, you can put like indexes, pedixes, like footnotes, and integrals, wild symbols that you can find online. You can use basically everything. You can define it, and then everyone that imports your file where you defined it will be able to use it. So if I define my crazy object as I know mathfrak f, I can use mathfrak f and Lean will know automatically what it is, as long as I'm, of course, as I opened that context. So as long as I've imported that file, because of course, if everything was global, then anyone could like dirty the notation of everyone else with their own like very specific and strange notation. But the widely used things like R are basically imported everywhere. So you basically have it from scratch.
So here in the hidden quantifier, the theorem goes for any of it.
Yes.
What if I explicitly quantify? What is different between this theorem and the theorem when I write A in R? Then I write all B in R and this.
Nothing. They're the same. They're exactly the same. They're functions.
I can get the lead.
Yes. They're the same also by you can I can take a theorem that's already written and used in other parts of the library. I can put the last argument from like the left of the column to the right of the column, and it's going to I put the for all. If I put the correct notation, so for all and then a comma, it's going to compile. Everything is going to be okay. Now it's a different story if I had implicit arguments. So if A and B were implicit, for example, now that becomes a little bit different, because if I put the roles, they're automatically interpreted as explicit arguments. So I have to provide them when I use the theorem. So in my next proof, I will use add subcancel. Now I have to write add subcancel A and B. If they were implicit, I could omit A and B, and I would just let Lean try to infer them automatically. But if I write the for all, I have to provide them. So I have to be careful with that notation. But for any other like use, it's completely the same. In fact, I mean, it's actually like in type theory, it's saying that like, the for all notation is just sugar syntax for a dependent type, for like a dependent arrow type, which goes from something and goes to P of something.
So I'm fully about the fact that there is not one proof, which is clearly not the case when mathematics, right? Because there are two that are useful because they should use and there are two that are useful because you should. If I ask Lean to show me the only proof of theorem, which proof you choose?
It will not show you a proof. I mean, if you ask it to show the proof of the theorem that's called add subcancel, it will give you the proof that's written under ad sub cancel, and there can be only one theorem with the same name. Of course, I can I can write another theorem which is called ad sub cancel prime, for example. I can write exactly the same hypothesis and thesis, and I can write a different proof. And then if I use that other version of the theorem, when I jump the theorem, it will show me the other proof.
So it's the one that write the theorem that choose the proof.
Yes, exactly.
So if you want to put in the library another proof of the same theorem, because I think is important, that's usually there are paper, another alternative proof of this theorem. I have to change name.
You have to change the name, or more likely, you will put it into you will not put two proofs of the same theorem in Mathlib probably. You will put it in some side project. There is the I think it's called the archive, where a lot of the projects that are interesting but are not will not be useful to people in the future, like to use inside their theorems. Because if I have two proofs of the same theorem, in practice, if I don't want to understand the theorem, I just want to use it for my own goals, it's exactly the same having one proof of the other. I mean, the theorem just takes the hypothesis and gives you back the thesis as a function which it is in that theorem. So we will not put two proofs of the same theorem in the library, but you're right, there are several proofs of some theorems in the library, not just not in the main one, in some side libraries. So if people want to, I want to know what is alternative proof, I can still go check it. It's still open source, and you can still contribute to it however you want. But if you're going to reuse it, this other proof in your project, you have to import the the side project. That's also because of if you have to import everything every time, you have to download a lot of data each time you have to start a new project. And Mathlib is something that you really want to import every time you start a new project. So the one goal is to keep it, I mean, as small as possible, meaning with the same number of results. It's better if it's small. Of course, especially if it has more results. So yeah, that's basically. But you can do different proofs. It still can give insights to different proofs because basically you choose the route to take. It's just that Lean will not understand that they're different. You will not know the difference. But as a mathematician, you know the difference and you can use it in this way.
So like when you write a proof, like your ultimate goal is for it to be implemented into Mathlib for people to use it, right?
Not necessarily. There's examples. Now we're going to see a few examples of projects. Not every project is a Mathlib. For example, there is like one of the most famous ones. Let's directly go to that. Is the liquid tensor experiment. Okay, that's a result which was like the formalization was encouraged by Peter Schulze. That's a result by Peter Schulze in condensed mathematics, and he basically said, okay, I'm not 100% sure about my proof. I did the proof, like nobody's willing to check it for me. It's a very complicated proof, and I cannot really wrap my mind around it. I think it's true, but I would like full certainty because it's an important result. So it challenged the community to try and prove it. They thought that it would take forever, like 2 years, but in fact, it was completed in just a couple of months. And they arrived at the result. So they said, okay, this result is true. Now we have the formalization that's true beyond any like reasonable doubt. Okay. But then do we need the result in Mathlib right now? The answer is no, because we don't have even the tools to talk about that result. We just have the single result, the rush to get to that result, but nobody would be able to use it right now because the library is not mature enough to do condensed mathematics properly. So for now, the project was done in Lean 3, because it was done a couple of years ago. And it remained for now in Lean 3 because porting into Lean 4 will be a huge port by itself. So there are results. Sometimes the goal is just to prove the theorem, just to make sure the theorem is real and to give a formalization of the theorem. And also to say, I mean, there's a lot of insight that's to be gained from the formalization of the results. Apart from the truth value of it. For example, this very example of the liquid tensor experiment during the formalization, the proof has been simplified. And that's that's very notable result because even the lead formalizer, which was Jan Commelin at the time, which was like the lead of this formalization project, because Peter Schulze did not touch the code himself. He helped a lot with the mathematics, but he didn't program it. Even so, the lead of the project said that he could only see 2 moves ahead in the proofs. He did not have a global view of the proof. He did not understand the proof globally, but he managed not only to formalize it, but to simplify the proof. It was not a one-man effort. It was a lot of people contributed to it. So many people helped in the project, and none of them understood the complete proof properly. Only basically Schulze and Clausen really understood everything, but they were still able to put it together to do stuff that was actually correct in the end, and it was better than the original result. So that's another reason why you would want to formalize something, even if it doesn't end up in Mathlib. But yes, most things we would like if they end up, if they're relevant. Okay, so if there's no other questions, we can have a quick look at a few formalization projects.
I have a question.
Sure.
When I want to check that the theorem is true, when I write the program, then I'm sure it's correct, and then I test. And most of the time, it doesn't do what it was supposed to do. So if I have to check a proof, I have to write a statement. Then I have to write a statement that is smaller and simpler and simpler. So everything at the end boils down to write definitions. So what Lean does is automatically check the inference rule implications. So if I'm sure about the definitions that they give and the statement, and then it's correct, and then it fits. The uncertainty is just maybe I give a wrong definition.
Yes, maybe I define the real numbers as the empty set, and then everything is true about real numbers. And maybe it's buried in like 40 definitions under. There's something that defines trivially, and then everything else doesn't make sense. So yes, definitions are probably the hardest part about the formalization. One of the hardest parts is giving the correct definitions for 2 reasons. One is the reason you just told me, which is, yes, I really need to make sure the definition is what I mathematically intended to do. And the second reason is we can usually define things in many different ways, which are mathematically equivalent. Not all of them will be formalization friendly. There will be some that will be harder to work with after. So you also have to choose a way of formalizing things, formalizing definitions that's easy to use after. So that's the hard part. That's one of the hardest parts of formalization. And yes, basically, once you have the definition, you're super sure about the definition. Now, what you mentioned before are also tests. Like in code, you do tests. You can also do some kind of tests for definition to check if it's correct, which is, can I prove things that I maybe not super hard things, but basic things which I know are true for that definition, which I expect them to be true for my definition. And if I can prove those basic things, well, I'm more and more convinced that my definition is indeed what I want it to be. So yeah, basically the only uncertainty there is in definitions. Of course, software is faulty. And Lean is software. So another comment is made is, well, I'm still relying on a piece of software, and software fails all the time. Why am I relying so much? Why can we put so much trust into this specific piece of software? And that's because the trust is not put in all the Lean language. Not all the Lean language is needed to check that the proof is correct. The only part that's needed is what's called the kernel, which I introduced earlier. And the kernel has 2 characteristics. It's small and it doesn't change 2 times. So it's not updated frequently. It's a piece of code that hundreds of people have checked. And we basically have to put our trust in all those people who have checked the code before us, but we can check it ourselves. It's a couple of hundred lines of code. It's not impossible to check. Of course, it's technical code, so it will not be easy if you don't know the language. Another thing which can make us even more certain about the validity of a proof, is that, so I talk about one kernel as if it's a single thing, and there is one kernel, which is like the standard Lean kernel. It's actually written in C++. It's one of the very few parts Lean that's written in another language. But there is a possibility of plugging an external checker. So an external kernel, which everybody can write. I mean, I can write my own kernel. I don't have the technical capability of doing it, but I could write if I had the technical capabilities. And there are a couple of external checkers. And it's very, very unlikely that if a bug is found in one of the kernels, then the same bug is found also in the others because they're implemented by different people in different languages. There is, for example, an external checker that's implemented in Lean 4. That's not it's strange because it's not the default one. But basically, if I put everything to the test in all these kernels, it's really, really unlikely that the result is false. Of course, since we're using computers, we can always have a gamma ray which flips one bit of the computer. I mean, it has happened in elections before, so it can happen in Lean. But the code is basically checked on every machine. So if I check my proof in my computer, and then some gamma ray for that particular instance flipped a bit, which made a false proof true, which is per se extremely unlikely, of course. Then will it happen again in my friend's computer, which I show the proof to? It's really basically impossible. So yes, there are of course false, but they're really extremely unlikely to happen.
Okay, so want to this question. If I want to define the real numbers, if I define them, then I put out some tests like I prove that the set of real numbers is non-empty.
Yes.
And that proof will sort of be a check that my definition.
Yeah, they are basically like unit tests in pure science. They do not give us the certainty that this object is the one we want, but they give us some sort of confidence.
Is it frequently this sort of unit test?
Basically, the unit tests in Mathlib are what's called the API of a theorem itself, because when you are of an object, which is all the collection of lemmas that are needed to use my definition. As I said before, once I write like the exponential function, I will write some lemmas about it, which are the basic properties of the exponential functions, maybe even not so basic ones. I know that the derivative of the exponential is the function itself. And basically, they're not written just because we want to test. They're written because we really need to use them later. So it comes up. It kind of goes with the usual formalization progress. Okay, we have like 5 minutes left, so I think I'm going to go into the website of this just to show you how a formalization project looks like. That's a bit outdated actually, but it's not too different from a project that started just a few months ago. This is the core of the project, which is called the blueprint of the project. Now the blueprint is a middle ground between the informal proof and the formal one. Let's see a little bit what's in there. That's just the index. Now the blueprint is basically an HTML document. It can be converted to PDF, which contains all the definitions and proofs that we are going to formalize. For example, here we have a couple of definitions. Here we have a mark. If you go into more advanced files, we have lemmas, and we have the proof of the lemma, which we can collapse or not. And basically, this is something which can be written by a mathematician who knows nothing about Lean. It's just a more detailed version of the paper itself, the mathematical result itself, which is more formalization friendly, which is it's more close to the actual formalization. Because of course, when you formalize things, since we have to give a lot of details, we also tend to split results into multiple parts and try to reuse if a proof contains some passages which are the same of another proof, we try to abstract them. Of course, this is done in mathematics also, but formalization is done more aggressively. And each result, this is linked to the lean code. So each result has, for example, this definition, we can click here on lean, and it tells us where are the declarations which correspond to this definition. We can click on them, and it brings us to the code, which corresponds to that definition. So it's useful for many reasons. It can help the people formalize the things, which, as I said before, usually do not know the full theory very well. Maybe they're completely new to theory, maybe they're experts in the theory, but they do not write the paper, so they do not know every single detail. So it helps people to orient themselves in the project. It's a way of communicating with the authors of the paper, or with the informal authors of the project. And it's also a way for us, after the project is complete, to explore how the project is going, or how the project is going if it's not completed, or how it's gone if it's completed. See the lean code, and a very cool feature of the blueprint is that it automatically builds this, which is the dependency graph of this project. Every piece, every node of this graph is either a definition or a lemma. And we see that they are linked. The arrows represent what theorems it depends upon. So for example, we know that this definition here, yes, if we click, it tells us the definition. So like this definition here depends on this theorem here. This lemma here needs this definition, this lemma, this definition, and this other thing here. And we can explore how it's going. Now, this is a completed project, but let's go to maybe a project that's not complete yet, the Carlson project.
The definition for the proof.
Usually either the definition of the proof or the proof, yes. Maybe there's, I'm not sure if there's probably a difference between, oh yes. Now, okay, yes, there's solid arrows and dotted arrows. Maybe solid arrows are like it's needed in the proof, and dotted arrows are needed in the statement, but I'm not 100% sure about it, so I may be wrong about this. But yes, this is all, yes, that's not automatically generated from the lean code. This has to be aligned manually with later codes. But this is how let's see.
So this is the flow chart of the theory.
Yes, yes. This is how the dependency graph of an uncompleted project looks like. You see there's different colors, and green things are things that are already formalized, while blue things are things that are ready to be formalized, but not yet formalized. So their dependence are there, but they're not formalized. White things are things that still need stuff like above them before they are even, we can start to formalize them. It's a way to see how the project is going, and also to choose if I want to contribute to the project. I can go here and say, oh, look here, there's something that's not being completed, but it's formalizable now. Let's see if I understand it. Maybe I do. Okay, let's try to understand the proof and formalize it myself. And I can do, and like everyone can do it. Even an undergraduate student can do it. Someone outside of academia can do it. Contribute to it. Push. Yeah, this is the blueprint. This is automatic. The graph is automatically generated from the blueprint. So from this.
The blueprint is a guide.
Yes.
You write your paper this way.
Yes, I mean you can usually it's something that's between the paper and the formalization. So you write the paper, then you put in a little bit more effort to write a more detailed explanation, which is the blueprint. And then someone else, or maybe you yourself, are going to formalize it, trying to follow. Of course, it's something that evolves during your formalization.
Need a special formalization.
The blueprint is basically just LaTeX with 2 or 3 special formats. You write a LaTeX file, and then for example, let's say I want to, okay, here I want to say this theorem correspond to this lean theorem. There's a command which where I can put just lean/lean. I put the name of the theorem in lean, and it will automatically link them. and I can write lean OK to write that the formalization is done, and it will put this check mark here. So yes, but it's basically all latex. There's literally 2 more commands.
Object are theorem definitions.
Yeah. Yes. Theorems, definitions, lemmas. Of course, now the blueprint doesn't need to contain everything that's in the formalization project. Maybe I have a very, very small lemma, which is super technical. I don't want to put it in the blueprint. It's going to be in the formalization. But in the blueprint, I just want the high level view. Maybe if we were to put everything, there would be like 1,000 nodes instead of. So yeah, that's something that can be decided by the maintainers of the project and whoever helps them to write the actual blueprint.
Sorry, but someone has to check that because it's a lot of everyone can contribute to a project like this, and maybe if I from the blueprint I have to write a definition or a lemma, but if I write it wrong, someone has to check that I write because maybe I've written a similar and still true lemma, but it's not the one that is in the blueprint.
Sure.
And someone has to check that.
Usually, writing definitions and writing statements is something that's mostly done by the maintainers of the project. You can write definitions or statements, but probably if you're not someone they know very well, they're going to like quadruple check that you did something that is meaningful. Because everything that's, usually projects are open source. You can do your closed source project, of course. You can depend on Mathlib. There's no problem. But open source project does not mean that everyone puts something and that something automatically goes in the project. There's still a layer of moderation. Usually the maintainers of the project, we need to approve your pull request. So I tell you, okay, I finished this lemma. I send it to the GitHub repository. Next time we'll see what it means. And the maintainers have to read it and click something to accept, and then it gets merged into the real project. But that's something that, again, is done basically in every open source.
Yeah, it's where the human can put some mistake.
Yes, writing wrong statements or wrong definition. But maybe the problem is in the definitions and like the last statement, like the real final result. Because if I made a wrong statement of a theorem, which is just a lemma somewhere in the middle, it's not a problem. I mean, it just will not be useful. Or maybe it will, because maybe it turns out to be useful, but in principle, I can write, if it compiles, it's true. So it's just a true statement that's in there that doesn't help, but doesn't even harm the project. If the final statement is checked and gets a complete proof, then that final statement is true. So whatever is in, and that's pretty rare.
That's clear, but write, you compile, and the output is wrong. You know it's true. So you have to come back and find.
But it doesn't tell you. Oh, it tells you that.
Yeah.
It tells you exactly where it's wrong. I mean, it doesn't just tell you, oh, you've made a mistake somewhere. In a few cases, the mistakes can be a bit cryptic, but generally it's quite easy to see where the mistake is and to pinpoint that part specifically. So it helps you in that also. I think we are out of time. I'm going to okay.